Now we will evaluate integral 0 to 2 pi cos theta d theta divided by 3 plus 2 cos theta using contour integration. Before proceeding with the solution, we will first understand certain things. If the function is given in terms of sin theta or cos theta and the limits are between 0 to 2 pi, we take z is equal to e power I theta. When you take z as e power I theta, then automatically dz will be I e power I theta d theta, and from that you can rewrite d theta as dz by Iz. So it is enough if you integrate this integral over c. This will be z squared plus 1 by 2z into dz by Iz whole divided by 3 plus 2 into z squared plus 1 by 2z. But of course, what is c? C is the circle mod z is equal to 1, with center at 0, 0 and radius 1 units. This will be common, contour will be common, but you have to check the limits are between 0 to 2 pi, and here you should have a function of cos theta or sin theta or a combination of cos theta and sin theta. So when I simplify this, this will be like this. Let me simplify this. Z squared plus 1 dz by, I will have 2z into Iz. 2z here, Iz here, this will be moved to the denominator. When I simplify the term in the denominator, before that these two gets cancelled here. I'll have z squared plus 3z plus 1, and the z will go up, 1z gets cancelled here. So the simplified integral will be z squared plus 1 dz divided by 2Iz into z squared plus 3z plus 1. Suppose if I take f of z as z squared plus 1 by 2Iz into z squared plus 3z plus 1. So I have to use any one of the contour integral to evaluate this particular integral. I can use Cauchy's integral formula or the Cauchy residue theorem, and out of these two the best one will be the Cauchy residue theorem. So now what I will do is I will use the Cauchy residue theorem, and I will find the value of the given integral. So now as usual, what will be your f of z? F of z, I have taken it as z squared plus 1 by 2Iz into z squared plus 3z plus 1. I have to find the singularities. Singularities of f of z are, I'll have z is equal to 0 and z squared plus 3z plus 1 is equal to 0. So now when I find the value of z here, I will have 9 minus 4 b squared minus 4ac whole divided by 2a, which turns out to be minus 3 plus or minus root 5 by 2. So I have three singularities. Z is equal to 0, Z is equal to minus 3 minus root 5 by 2, and Z is equal to minus 3 plus root 5 whole divided by 2. And I have to check out of these three singularities, how many of them lie inside C. And what is C? C is mod Z is equal to 1. So obviously you can see that Z is equal to 0 lies inside C. Z is equal to 0 lie inside C. Okay. Now you take the other one, root 5 minus 3 by 2. Okay, one of the roots. Now what I will do is, I will multiply and divide by the conjugate of the numerator. 2 into root 5 plus 3, and I have to multiply this with root 5 plus 3. This will be 5 minus 9 divided by 2 into root 5 plus 3. Okay. So this will be minus 4 by 2 into root 5 plus 3. Okay. When I take the absolute value of minus 4 by 2 into 3 plus root 5, this will be less than 1. Obviously, because here I have 3 into 2, 6. 6 is greater than 4, so absolute value will be less than 1. So Z is equal to minus 3 plus root 5 by 2 lie inside C. Okay. So when you have this and you know that in a quadratic equation product of the roots is 1. Okay. So when one of the root has got absolute value less than 1, the other root will have absolute value greater than 1. So obviously minus 3 minus root 5 by 2 will lie outside C. So out of these three roots, 2 lie inside C. I am going to use the Cauchy residue theorem, and what I am going to do is I am going to find the residue of f of z. So in this case, what will be residue of f of z at z is equal to 0? This will be limit z tending to 0, z into z squared plus 1 by 2iz. So I have to multiply this with z with f of z. So I will have z squared plus 3z plus 1. This z gets cancelled here, and I get the value as 1 by 2y. So residue of f of z at z is equal to 0 is 1 by 2y. Okay. So before evaluating the residue of f of z at minus 3 plus root 5, I require certain calculations which we will do now. Suppose if I assume alpha as minus 3 plus root 5 by 2 and beta as minus 3 minus root 5 by 2. I calculate alpha minus beta. This will be minus 3 plus root 5 plus 3 plus root 5 whole divided by 2. These two gets cancelled and I will have root 5. Okay. So alpha minus beta is root 5. You keep this in mind. So now what I have to do is, now I have to calculate residue of f of z at z is equal to residue of f of z at z is equal to alpha. This will be limit z tending to alpha, z minus alpha into z squared plus 1 by 2iz into z minus alpha into z minus beta. So these two gets cancelled here. I will have alpha squared plus 1 by 2I alpha into alpha minus beta. Now what will be alpha squared? Alpha squared will be root 5 minus 3 whole divided by 2 the whole square plus 1 by 2I into root 5 minus 3 whole divided by 2 into root 5. Okay. So this 2 and this 2 gets cancelled here. And when I expand this, I will have 5 minus 6 root 5 plus 9 plus 4 whole divided by 4I into, this will become 5 minus 3 root 5. Okay. When I simplify this, this will become 13 plus 5 18. 18 minus 6 root 5 divided by 4I into 5 minus 3 root 5. Okay. When this will be 5 minus 3 root 5. This one is right. So when I remove 6 here, I'll have 6 into 3 minus root 5 divided by 4I. Okay. So now what I will do is I will remove this root 5. I will have root 5 minus 3. Okay. So when I strike out these two, I will have minus 1. So this will be minus 3 by 2I root 5. So the value of integral over C f of z dz, this will be 2 pi I, okay, into 1 by 2I residue for 0, and this will be minus 3 by 2I root 5, which turns out to be pi into 1 minus 3 by root 5. So the value of the given integral will be pi into 1 minus 3 by root 5. With this, we complete the evaluation of the given integral.